Hi, Advanced Algebra 2. This is Mrs. Langford. We're going to now solve quadratics by graphing and square roots. So up until now, we have been graphing and writing equations of quadratics, but now we're going to solve them. But it's related to something that we've been doing. The solutions of a quadratic equation are the points where it crosses the x-axis, if it does. So there are many different ways that we can call the solutions of a quadratic. So the first way is the way that we've been talking about as far as with graphing. We've been talking about it in terms of x-intercepts. So the solutions of a quadratic are the x-intercepts. And we've thought of those as the point P and Q. That's a 0, P0, Q0. In this section, we're going to refer to them as solutions. And when we do that, we're just going to list them as numbers. So x equals a number. Now, we have three different situations. A quadratic can have one solution, where it's crossing the x-axis once. So that would be where its vertex is just touching down. So one solution. Or it can have two solutions, where the parabola is crossing the x-axis twice. Or it could have no solutions. Or actually, it's no real solutions. So that is where the parabola will never cross the x-axis. So one solution, two solutions, or no real solutions. So if you look at the information that I've included from the book, it shows that we're going to work with these in standard form with those constants A, B, and C that we've worked with before. It also introduces another word that can be used in place of a solution. So where it crosses the x-axis can also be called the root. So let's just review. When we say the roots of a quadratic, that's the same as the solutions of a quadratic solution, which is also the same as the x-intercepts. They all tell us what x is doing when our y value is 0. So in this video, I'm going to cover the first two methods of solving quadratic equations that you see listed in this graphic. So we're going to look at by graphing. Now we're not going to do a lot with this because you have been graphing a lot up until now. And so now we're just going to graph a few and look at where it crosses the x-axis, or we're going to look at the x-intercepts, and those will be our solutions. The second method is when a quadratic is in a certain format. Then we can use square roots. So when it's in the format u squared equals d. Now that's kind of strange to think about it, but when you have, let me write it this way, just an x squared, so you don't have a single x, or just an x squared expression. And so you don't have a single x. We can solve by using square roots. And then later on this week, we'll talk about solving by factoring. So in example 1, number 2, we've got an equation in standard form. Notice that it is set equal to 0. This is going to be a little visual cue from now on that we want to solve it. So remember that what we're looking for is what x is when y is 0. So if your equation is set equal to 0, that means that they have let y equal 0. Then that's a cue that we are definitely solving along with the directions. So to graph it, that's one method to solve. We can pick out A, B, and C, and then find the vertex. So we take the opposite of B divided by 2A, and then plug that in. So you can see our vertex will be 1.50. Now I notice right away that I've got my solution. This is the x-intercept, and this is where the graph is crossing the x-axis, so this is my solution. So if it's the vertex, I'm only going to have one solution. So I'll just graph 1.5, 0. And then I found 2 more points. So I went to where x is 2.5, plugged it in, and found that y is 4. And then where x is 1/2. And so this should be a graph that is narrow, is opening up, and has one solution. So we say that our solution is x equals 1.5. So that's how we list it as a solution and how we use graphing to help us solve. So now let's graph number 3. So to graph number 3, notice it's not in standard form. So the first thing we need to do is arrange it into standard form. So use the rule to move your terms over to the side where the x squared is. So we're going to move everything over to the left side of the equal sign. And we'll end up with 1/2 x squared minus 6x plus 20 equals 0. Pick out A, B, and C, and then find your vertex. So our vertex is at 6, 2. Now if you think about it, 6, 2, that's in the first quadrant, or that upper right. And if you look at the equation and think, gosh, does this open up or down? Well, it's going to open up. So that means that this parabola, we can anticipate that it is not going to have any real number solutions. No place where we can see it cross the x-axis. So if we go ahead and graph those 2 points, 5, 2.5, and 7, 2.5, we can see that it's just going to hang up in that first quadrant, and so that it will not cross the x-axis. So we have no real number solutions. Now before we look at our next method, we're going to talk a little bit about square roots. Sometimes when you solve a quadratic, you end up with the square root in your answer. So unless you are asked to estimate the square root, for example, the square root of 3 is not an even number, we are simply going to simplify it instead. When we simplify, that means that if the number is a perfect square, we go ahead and take that square root. So for example, if it's the square root of 9, we know that the square root of 9 is 3 or negative 3, and we want to know both places where it's crossing the x-axis. So we would simplify that as plus or minus 3. But if it's not an even square root, like the square root of 24, we need to break it down into factors, and any factors that are perfect squares, and then take the square root of any of those perfect square factors. So first of all, look at your square root and ask yourself, is it a perfect square? 24 is not, but we can break it down into, well, let's think of different factors. So 2 and 12, neither of those are perfect squares. 3 and 4. And it's a good combination when one is not a perfect square and one is. 3 and 8. Neither of those are perfect squares, so let's try 4 and 6. There we go. That is our pair. So we're going to break this up and think of it as the square root of 4 times the square root of 6. Now what I'm doing is just little factor tree branches. And then I'm going to take that square root of 4. Now I still have my plus or minus sign. When we actually do the square root operation, then the square root goes away. Just like if we add numbers together, once we add them, the plus sign goes away. So when we take the square root of 4, then the square root sign goes away. The square root of 6 does not have an even square root, and it doesn't have any factors that are perfect squares. So we have to leave that. in its square root form. And so this is the simplified answer of plus or minus the square root of 24. Now on our next one, let's say we're solving a quadratic and we end up with plus or minus 2 times the square root of 80. So 80 is not a perfect square, but it's got some factors that are. So we can think 1 and 80, 2 and 40. Neither of those are perfect squares. 3 doesn't go into 80. 4 and 20, but I'm going to keep going. I'm going to divide it by 5 because I can see that 5 times 16. So I'm looking for a factor pair where I have the biggest perfect square possible. Now I already have a 2 out front. I'm going to take the square root of 16 and I have to multiply by whatever is out front already. I can't take the square root of 5. So I'll end up with plus or minus 8 once I multiply those times the square root of 5. And lastly, let's say we're solving and we end up with plus or minus the square root of 35. We think, I wonder if it has any perfect squares. We think about its factors, 3, no, 5 and 7. And we can't come up with any perfect squares factors. So that is simplified. Now sometimes you're going to end up with a number in your denominator and you'll have to take the square root of that fraction. You will get a square root in your denominator. So in that case, there is a math rule where we don't want to leave an irrational number in our denominator. So for example, we could think of this as the square root of 36 divided by the square root of 3. We could simplify that to 6 over the square root of 3. Now if you put the square root of 3 on your calculator, you can see it's an irrational number. It's the decimal 1.732 and it just keeps going. It doesn't end and it doesn't repeat. So a long time ago, mathematicians decided it was too messy to divide by an irrational. So they developed a method where we call rationalize the denominator. To do that, you're going to multiply the numerator and denominator essentially by 1, by that square root that you see in the denominator. Notice that that is the equivalent to multiplying by 1. It's not going to change the value of the expression. It's just going to change the looks of it. So up top, we'll get 6 times the square root of 3. We can't combine those. And then the square root of 3 times the square root of 3. We can multiply those numbers together. So it's the square root of 9, which simply reduces to 3, plus or minus 3. So this would be that answer, rationalize, meaning there's no irrational number in our denominator. All right, in your notes, this is a graphic that shows how we're going to solve quadratic equations algebraically. So we know we covered graphing, and now algebraically we're going to solve them by using square roots. Okay, let's try that one more time. So I'm going to cover that in this video, and then that's all. And then later in class, we're going to look at these other 3 methods. They may sound familiar to you. You may have had them before. We're going to cover them more in depth. Now, when we solve them algebraically and we're using square roots, then we need to know the properties of square roots, which is some of the things that I was just covering. And then just to reiterate what we were talking about, when a radicand in the denominator, so that means what you've got this in your denominator, is not a perfect square, so 3 is not, you multiply the fraction by the appropriate form of the radical. So you just multiply by that same radical, both top and bottom, to change the look of it. So you no longer have an irrational number in your denominator. So now let's go ahead and solve using square roots. So This method is used when you just have special forms of your quadratic equation. So you've got, now we don't have y, but we'll have x squared, just an x squared term, equaling a 0, or an x squared expression, some number. All right. So what we want to do is we want to isolate that expression. So here we would just add 31 to both sides, and then just keep solving. So x squared equals 20. Now, to work backwards from something that is squared, we can take the square root. 20 is not a perfect square, but we can break that up into the square root of 5 times the square root of 4. If we simplify the square root of 4, then we'll get 2 times the square root of 5. This is the two places where our quadratic is crossing the x-axis. So these are the solutions. Positive 2 times the square root of 5, negative 2 times the square root of 5. Now with b, let's subtract, and then let's divide. So then we would take the square root of both sides. Now when we have a square root of negative 3, or any negative number, then we can say that there are no real solutions. We will get to complex numbers where we can simplify that and show the imaginary solution. But when you have a negative under your square root, it would be no real solutions. Now C, let's start by multiplying each side by the reciprocal. So x plus 3 quantity squared equals 25 halves. We'll take the square root of both sides. So the square root of an expression squared is just that expression. And we'll get plus or minus square root of 25, which is 5, over the square root of 2. Now, before I subtract my 3 to finish my answer, I'm going to rationalize this by multiplying top and bottom by the square root of 2. So I'll have plus or minus 5 times the square root of 2 over 2. And then finally, I want to subtract 3. When I have a plus or minus expression, I always put it at the end. So I'm going to start with my negative 3 plus or minus 5 times the square root of 2 over 2. And that's how I would write the exact answer of the solutions to my quadratic equation. So one of them is negative 3 plus 5 times the square root of 2 over 2, and one of them is negative 3 minus 5 times the square root of 2 over 2. Now for the last thing, practice rationalizing the denominator. So pause the video, rationalize the denominator, and then come back and check your work. So you can see the answers to 1, 2, and 3. First one, you split up those square roots and then rationalize the denominator. If you have a square root times another square root, you can multiply those roots together. So we'll get the square root of 26. Just make sure that you can't break it down into any perfect square factors, which you can't. Number 2, you simply take the square root of the top and the bottom, and you'll end up with plus or minus the square root of 15 over 2. And then finally on number 3, square root of 5 over the square root of 3, and then just rationalize that denominator. So you end up with the square root of 15 over 3. Make sure that you mark any questions that you have on the notes, and we'll go over them first thing in class tomorrow, and then just practice solving quadratics using square roots, and then working with properties of square roots as we do that.